Alright guys, welcome back to the last video of the RC circuit analysis. Today we're going to be going over our series parallel circuits, and we're going to run through two different circuits to kind of give you guys examples and practice in setting these guys up and solving them and getting down to the final answers. So here's our circuit. We have a generator that is putting out 17 volts peak, and it is operating at 364 hertz. Coming up next, we have R1, which is 390 ohms, connected to C1 at 470 nanofarads. That is now going to branch into our parallel network. R2 is in one branch. On branch B, that has 110 ohms. Capacitor 2 is 390 nanofarads. And then moving over to the other parallel branch, we have R3 and C3. R3 is 820 ohms and C3 is 270 nanofarads. The things we're going to be looking for today are, you're going to have to pretty much solve for most of these anyway to get the answers. Some of these breaking down, the VR2s, VC3s, things like that. Sometimes we won't necessarily have to calculate all these values, but we're going to do it anyway. Just to give you guys the practice and the experience to see what are we looking at. Depending on what we're looking for, sometimes we don't have to worry about solving down to individual components. We can just look at the parallel branches and go from there. So the things we want to look at is, we're going to solve for our capacitive reactances for capacitor 1, 2, and 3. We're going to solve for the impedance from A to B, which is R1 and C1, just this series section right there. We're going to solve for the impedance for ZB, which is just branch B right here from B to ground. We're going to solve the impedance for branch C from C to ground. And then we're going to look at our total impedance across the entire circuit. Once we get that value, we can then go through into some of the more calculations that we have. We can solve for our current total. Then once we have our current total, we can go through and we can solve for our voltage drops. So I'm going to rearrange these real quick just because that's the way they're in order of how we're going to solve them and not just everything. So we're going to solve for our current total first. Then we're going to solve for the voltage drop across R1. We're going to solve for the voltage drop across capacitor 1. And then we're going to find the voltage drop across B to ground. Now, remember, the voltage drop across B to ground is going to be the same as from the voltage drop from C to ground because they are in parallel. So they're going to share the same voltage, same magnitude, same phase angle, everything. Once we have those solved for, we can then solve for the current going through branch B. We can solve for the current going through branch C. And then once we have that, we can also solve for the individual voltages. So then we can solve for the voltage from R2, the voltage across the capacitor 2, the voltage across R3, and the voltage across capacitor 3. So that's kind of the order of the way we're going to be solving these guys. Now, the first step that we need to do is we need to solve for the capacitive reactances. Now, remember our base formula for this capacitive reactance is solved as 1 over 2 pi times the frequency times the capacitance value. So we just plug these values in because everything is known at this point. So our capacitive reactance for capacitor 1 is 1 over 2 pi times our frequency, which is 364 hertz, multiply the capacitor, which is 470 nanofarads. We plug that into our calculator, and the reactance for X of C1 is equal to 930.295 ohms at an angle of negative 90 degrees. Now remember, when we're dealing with these guys, we have this relationship. So our X of L is at the top, our X of C is on the bottom of that axis, and our resistor values are here. Anytime we have a pure resistance, it's at 0 degrees. Anytime we have pure capacitance, it's at negative 90 degrees. And when we get into inductors, this will be at a positive 90 degrees for the phase angle, for just the inductive. So now we have our value. So we were able to come up with this formula, spits out the 930.295, and it's at negative 90 because all it is just capacitance. So we have this value right here. So there's our first value, capacitive reactance for capacitor 1. Now we're going to go through and we're going to solve for the capacitive reactance for capacitor 2. So again, we have the same formula, 1 over 2 pi times our frequency, which is 364 hertz, multiplied by the capacitor 2 value, which is 390 nanofarads. Now, when we decrease the capacitance, we should see an increase in our reactance. Remember that inverse relationship. So the capacitive reactance of cross capacitor 2 comes out to be 1121 ohms at negative 90 degrees. Now, capacitive reactance for capacitor 3, again, 1 over 2 pi times 364 times 270 nano. Plug that into our calculator, and our capacitive reactance for capacitor 3 comes out to be 1619 at negative 90 degrees. So 1,619 ohms. Perfect. So now we've got our capacitive reactances for those first three problems. So we have him, him, and him. Now we need to come back, we need to look. Okay, we want to find the impedance total between point A and B. So I'll just go ahead and switch colors again so we show that we're into a different step. So now the capacitive reactance, we're going to add these two guys together for their impedances. But the problem is we only have them in polar form. To add and subtract, we need to have things in rectangular form. But we can quickly convert those. Okay, so remember, coming back to this value here, so if we have our relationships, so if we're at negative 90, that means we're straight on this axis going up and down. We have no real component. It's all imaginary. So in this case, the impedance for A to B is going to look at this for our formula. So the impedance so it's going to be equal to the impedance of R1 plus the impedance of capacitor 1. Now R1 is pure resistive, there's no capacitance in it, so when we look at this guy, we're going to have 390 plus J of 0, because there's no capacitive component to it. So that's how we write the impedance of that in rectangular. We have the impedance of capacitor 1, which is 930, which, forgive me, it has 0 resistive components, and then a minus J because it's on the bottom half of the y-axis on this, of 930.295. So once we have those, now we're going to add them together, and we add them together by adding together the like terms. So we have our real apologize, my pen decided it's not going to work. There. All right. So we're going to add the real components together. We're going to add the imaginary components together. So the total impedance that we have from point A to B simply becomes the 390 minus J of 930.295. Now we're going to be using this value later, so we can also convert this into our polar equivalent at the same time. So we have this value here, and let's calculate it into the polar. So let's convert it into polar. And remember, that's going to be the square root of our real value squared plus the imaginary value squared, and the square root of that. And it's going to be at an angle of the arctangent of the plus or minus J over the real value. And that'll give us our angle. So this converted down ends up being 1.009K at an angle of negative 67.256 degrees. So those are our two values. So ZAB is equal to both of those values. One's in rectangular form, one's in polar. Okay, now we need to go through and we need to solve for the impedance of our other two sections. So the impedance of B, if we look from B to ground, we just have a resistor and a capacitor in series. So that makes it easy again for us as well, because we're just going to add those together. And so when we do that, we end up with the 110 ohm resistor and the impedance of capacitor 2 is 1121. So that's how it looks in rectangular form. Then we want to convert it into polar. So again, we apply the same formula as we did before, and we end up with 1126 at an angle of negative 84.396 degrees. Now, one thing we can kind of check to make sure our angles are coming out correctly is we got to look at the relationship between the two values. So for ZA and B, when we look, we have 390 ohms and we have 930 ohms of resistance. So it's going to be a lot more capacitive than it is resistive. So we should see this value start swinging towards the 90-degree angle. And this value is much bigger than when they're equal, so it's not going to be the negative 45. We're going to keep going past that. And so we get back down to this negative 67 degrees. On this one, on ZB, when we look at it, we have 110 ohms versus 1100 ohms of reactance. So this thing is going to be very, very capacitive, and it's going to be the vector is going to look like this. It's going to be a lot steeper than this guy, which is going to look more like that. So here, this is our theta, which is right there. This is our theta, which comes out to be this value. So depending on which one's bigger, and if it's a lot bigger, less bigger, we should see the swing either getting closer to 0 or closer to 90, depending on which one is larger. So there is our impedance for B. So the last one we need to do is the impedance from C to ground. And again, we come back and look, and our circuit is just R3 and capacitor 3 in series, which makes our life, again, a whole lot easier. So we have the 820, which is the resistive part, minus J, because we're dealing with capacitors, of 1619. That is going to be our angle, or I mean our impedance for that branch. 820 ohms of resistance and 1619 ohms of reactance. Again, we're going to want to convert this guy into polar. So following this equation again, we come out to be 1815 at an angle of negative 63, 138. And the reason the impedances I'm wanting both of those is because remember, when we get going, when we have things in series, we're going to add them together, so we're going to want them in rectangular form. When we're multiplying and dividing, doing our other electronics functions, we want them in polar form so we can multiply and divide. And so these two we're going to want to have in both forms because we're going to use them both pretty quick. And I'll show you that here in just a second. So now we have our three impedances. So we have this impedance, we have this impedance, and this one. So we have A, B, B, and C. Now we have to come up with a total. So if we look at our original circuit, we know that we have resistor 1 and capacitor 1 are in series. Then those are in series with the combination of the impedance on B and C in parallel. So when we write out our formula, our Z total is going to be equal to ZAB plus ZB in parallel with ZC. Just like what we've been doing with any other circuit, we have to find out what's in parallel, what's in series. So the B and C are in parallel, they'll be added to the total. So that's why I wanted to keep these guys in here, because when we combine them together, this one for ZAB needs to be in rectangular so we can add those values together like we would normally in series. Okay, so let's get to solving this guy. So this right here, we're going to call this our Z parallel total, just to kind of reduce things down and reduce the amount of letters, the amount of writing. We're going to designate it as our Z parallel total, and we'll solve it as such. So when we look at it, we're going to solve this the exact same way we did parallel. So our Z parallel total is equal to 1 over the impedance from B added to 1 over the impedance from C. Just the reciprocal formula. So now, just to kind of simplify our lives a little bit more and get rid of all these extra reciprocals, we're going to apply the reciprocal to both sides. So we change this guy from our impedance to admittance, which remember is the opposite. And all we're doing this is so we can make this equation a little bit easier to look at instead of having a whole bunch of stuff. So now this is the equation we're looking for, which is missing one of those parts because we've already taken it into account. So now we're going to continue on. We're going to add in these values, and now we're going to solve for them. So the admittance total that we have is equal to 1 over 1126 at a negative 84.396. That's going to be added to the impedance of C, the reciprocal of that, which is 1815 at an angle of negative 63.138 degrees. Now we just go through and we do the math. Now again, we want to use the polar versions of these because we are wanting to have the we're doing division, so we want these guys in polar notation, not rectangular. So now we're going to go through and we're going to do the math and solve these guys down. So we take the reciprocal of 1126, and this ends up being 888.099 micro at an angle of 84.396. And then the other one ends up being 550.964 micro at an angle of 63.138. So now when we look at these guys, the next step that we need to do is we have an addition sign right here. So we have to convert both of these values into rectangular notation so we can add them together. So remember, when we're converting back and forth from these guys, we're going to take, for the real value, it's going to be equal to the magnitude times the cosine of our angle. The imaginary value is going to be the magnitude times the sine of the angle. And now remember, this is our magnitude, which I'm just labeling as Z. This is our theta over here. So we're going to apply this formula to both of these equations. And so when they come out, we're going to end up with, so after we convert these guys, we're going to have 86.725 micro plus J of 883.854 micro. So that's this first one. Okay, now we're going to add that we're going to convert this one into rectangular using the same formulas. We just use its values instead. And this ends up being 248.949 micro plus J of 491.514 micro. So we end up with these two values in rectangular notation. Now, just like we did before, we're going to add them together. So real values are going to add to real values. Imaginary values are going to add to imaginary values. So when we do that, we end up with the total for this guy is 335.674 micro plus a J of 1.375 milli. So that is our final admittance total. So we have 335 microsiemens of admittance, and we have 1.375 millisiemens of admittance. So add them together, that's our total value. I'm sorry, this is conductance and this is susceptance. I apologize. I'm trying to get the names right. But just to understand, that's what we're doing. This is our resistive part, this is our capacitive part, so they do have different names. So now we have, when we're looking, we want to get back from our admittance into reactance, or impedance, not reactance. So we want to go from admittance to impedance. So this value we're going to have to take the reciprocal of again, which means we're going to have to divide. So once again, we have to take this value and we have to convert it into polar so we can do division with it. So when we take this into polar, we end up with this value being equal to 1.415 milli at an angle of 76.281 degrees. Now, to get them back, we take the reciprocal of both sides, and when we do that, we get back into our impedance total, which comes out to be 706.714 ohms at an angle of negative 76.281. So now that we have those, we have to go through, this gives us our parallel part. So now we need to finish up. So the total impedance that we have, remember, is our impedance from AB plus the impedance of our parallel branch, which we just solved for. But remember what I said, these guys are not in rectangular, or you have to add in rectangular, this guy's in polar. So we have to convert him into rectangular. And when we do that, we can add these guys together. So our parallel impedance that we have, we convert that into rectangular, and that comes up to be 167.605 minus J of 686.552. So then when we're done, we'll add these together. So our ZAB, so our Z total, is equal to 390 minus J of 930.295 plus this value here, because that's that's the impedance in rectangular. And again, we got to cut this down into one value. So we add the like terms together. And our impedance total comes out to be 557.605 minus J of 1617. So now with the reason that we have this, we're going to use this value and we want to find our current with it. So we're going to have to convert this guy back to polar. There's a lot of conversions, I know. And so when we do that, our Z total comes out to be 1.710 K at an angle of negative 70.974 degrees. So this is our final value for our impedance. There was a lot of work to get here. That's the majority of the work during these guys, is converting these back and forth between polar and rectangular, and understanding that when we're adding and subtracting, we want the values in polar, and then if we have to convert them back and forth, and then we want values in polar when we add or subtract. So now, once we get to this point, we can solve for the rest of our values. So we can solve for our current total. So I'll come back up here and I'll show you our list. So now we have our impedance total as well. So now let's start solving our next set of things. So the next one we want to solve for is our I total. Remember, our I total is equal to the voltage total divided by the impedance total. Okay, so we start off with 17 volts peak at an angle of 0 degrees, and we divide that by our impedance total, which is 1710 at negative 70.974. We do the math. Our current total comes out to be 9.942 milliamps at an angle of 70.974 degrees. Now that we have that total current, we can then solve for the voltage drop across R1, voltage drop across capacitor 1, and then find the voltage drop across the parallel branch. So VR1 is equal to the current total, because that's what it has going through it, multiplied by the resistance of 1. So we have 9.942 milliamps at an angle of 70.974. That's going to be multiplied by our resistance value, which is 390 ohms at an angle of 0. So the voltage drop across R1 comes out to be 3.877 volts at an angle of 70.974. Then we're going to solve for the voltage drop across capacitor 1. I total times our reactive capacitance value. So we have 9.942 milliamps at an angle of 70.974 degrees times our capacitive reactance for 1, which is 930.295 at an angle of -90. The voltage drop across capacitor 1 then is equal to 9.249 volts at an angle of -19.026 degrees. Then the last part we need to do is find the voltage drop across our parallel network. So again, we have our current total, and that's multiplied by our impedance of the parallel network. And since we've already found that, we don't have to do it again. So again, we take the 9.942 milliamps at the 70.974 degrees, and we multiply that by our parallel impedance, which is 706.714 at an angle of -76.281. So the parallel voltage that we have, and I'm just labeling as VB because that's the first letter we hit to, comes out to be 7.026 at an angle of -5.307. So this is what we would measure if we put our probe across the parallel branches and sent it to ground. This is what we would measure, 7.026 at this angle. Now that we've got these voltages, so if we come back and look at the very top, we have this voltage, we have this voltage, and we have the voltage from there to there. Now, one of the things we can do at this point is we can do a double check to make sure we've done our math correctly and we're getting the correct values. So again, we're going to come back and we're going to do a Kirchhoff voltage loop. That way we're not solving the entire problem and realize we made a mistake. So with that, we have the voltage drop across R1. So remember, if we go around in the circle, that's going to be added to the voltage drop of capacitor 1 plus the voltage drop across the parallel network minus the voltage source has to be equal to 0. Okay, we're going to rearrange this so that the voltage source is on the other side, and we'll get down to solve this guy. So what we have is 3.877 at an angle of 70.974 plus the voltage drop of our capacitor, which is 9.249 at an angle of -19.026 plus the voltage drop across the parallel branch, which is 7.026 at an angle of -5.307 is equal to 17 at 0. And I just did that by moving our voltage source over to the other side. So now again, we're looking at this equation, and we notice we are adding. So we have to have our values in rectangular form to add them together. So we're going to go through and we're going to convert each of these guys into rectangular. And we do, or after we do, we end up with 1.264 plus J of 3.665 for the first one. For the second value of our capacitor, which this is the other reason why we've solved for these guys both back and forth. So we have 8.774 minus J 3.015 plus 6.996 minus J of 0.649, and then this one's an easy one. It's 17 plus a J of 0. Okay, so like I said, all we're doing is we're just adding and subtracting these guys, so we have to take the polar voltages and convert them into its rectangular equivalent. That's why we're doing these in the lab, is to get used to converting these back and forth depending on the situation. And we're adding, so they have to be in rectangular. So again, we're going to combine like terms together. So all the real values will get combined together. All the imaginary values will get combined together. And when we're done, we should see them equal to 17 plus J of 0. Okay? So we add up 1.264, 8.774, and 6.996, and that gives us 17.004. And then we add up all of our J values, and we end up with a plus J of 0.001. Now, for all intents and purposes, those two are equal. We're talking about 4/1000ths of a difference between them on the real value, and 1/1000th left difference between the J value. So since these guys come out and they are essentially equal, so our KVL equation is equal, we're good. So we know we can safely continue because we have the correct voltage drops. We didn't get anything weird. Earlier when I was doing this, I dropped some values the first attempt that I went through it. And in the end, I had values that were not equal. So I knew that at some point it screwed up. So I went back through and found out where it was. So now that we have this part completed, we know those voltages are good, we can continue to solve for the rest of it. So we'll kind of scroll back up here to the top. So we found our current total, the voltage from R1, voltage from C1, the voltage from B, and then here we did a Kirchhoff voltage loop check to make sure that we were on the right path, which we are. Now we can go through and we can solve for the current through IB and the current through IC because we know the voltage of each of those parallel networks. So we'll change colors again. We'll come back down to our section again. So we want to solve for IB. So IB is equal to the voltage of the parallel system, which we've labeled as VB, divided by the impedance of this. So we have 7.026 volts at an angle of negative 5.307 divided by the impedance of B, which is 1126 ohms at an angle, of negative 84.396. Now remember, when you're dividing your angles, you subtract. So in this case, we would have a negative 5.307 minus a negative 84.396. Watch out for that negative sign and this minus. They will screw you up. So this ends up, our current that we have through B is equal to 6.24 milliamps at an angle of 79.8089 degrees. And then for branch C, we're going to do the exact same thing. We have the voltage of the parallel system divided by the impedance of C. So 7.026 volts at an angle of negative 5.307 divided by the resistance of this guy, which is, sorry, I lost it in my notes. Now my pen's disconnected. So 1815 at an angle of negative 63.138. So we solve that, and we end up with our current total for both of these, or for C, is equal to 3.871 milliamps at an angle of 57. Oops. At an angle of 57.831 degrees. Now that we have those two currents, now it's time to make sure we did that correctly. So let's do another double check. But this time we're going to use Kirchhoff's current law. So remember, our I total has to be equal to our current going through B plus the current going through C. So we are going to take a step back and look at this. And so we have our I total. So we have 9.942 milliamps at an angle of 70.974. And these are just coming from the values that we found previously. Our IB is 6.24 milliamps at an angle of 79.089 plus 3.871 milliamps at an angle of 57.831 degrees. So now we're going through, and again, we're adding these guys together, so we have to convert all of these guys into rectangular, because we have to add and subtract in rectangular notation. So we'll go through and we'll convert these guys down. So this one, so our I total becomes 3.241 milli plus J of 9.399 milli. Then it's equal to 1.181 milli plus J of 6.127 milli. So that's this value converted. That's this value converted. And then we're going to add that together. And then with this last one we get is 2.061 milli plus J of 3.277 milli. Oh, excuse me. This one right here, this is a negative. When I wrote that down wrong, I dropped my negative sign. This is at a negative 79.089, which means this is a negative J. Otherwise, the math's not going to work out right. Or did I write that down wrong? I think I wrote it down wrong on my notes. Nope. I did have it right the first time. That current has a positive angle, that current's a positive angle, and our total current's at a positive angle. I apologize for the confusion. This is how it's supposed to be. Positive 79 degrees, positive J. So again, we're going to come down here. We're going to add like values. So we're going to add the real values together, and we're going to add the imaginary values together. So we have 3.241 milli plus a J of 9.399 milli. We add the real values together, and we get 3.242 milli plus J of 9.404 milli. Now again, these guys are close enough. They're within thousandths of each other. We're still well within the 5%. So these guys are equal. Therefore, we good. We've proved that our equations are correct. So now, the last step that we have to do is go through and we need to solve for our voltages. And we do that. So the voltage of R2 is equal to the current B, because that's what branch it's in, times our R2. So we get 6.24 milli at an angle of 79.089 multiplied by R2, which is 110 at 0. So the voltage of R2 is equal to 6.995 at 10.911 degrees. The voltage for capacitor 2 is equal to the current through B times the reactance value of capacitor 2. So we have 6.24 milli at 79.089, and then that is multiplied by the X of C value for 2, which is 1121 at negative 90. So the voltage drop across capacitor 2 is equal to 6. Oh, I apologize. I did this math wrong. I looked at the wrong part of my notes. So on the capacitor 2, the 6.24 milli times 1121 is the 6.995 at an angle of negative 10.911. I completely botched this. I am so sorry. I was looking at my notes and I looked at the wrong thing. So this one is that 6.995 at negative 10. Then when we go, let's go back and look at R2, because I didn't multiply these together correctly. This ends up being 0.686 volts at 79.089. Again, I apologize that I did do the math correctly on my paper, just transferring from my notes to here I goofed. I'm real sorry about that, which we should expect. So if we come back and look at our voltages, okay, we have 110 ohms versus 1100 ohms. So we should see the majority of the voltage being dropped across capacitor 2, which is what we're seeing here. It's dropping almost 7 volts. This is dropping almost a little over half a volt. We can go through and we could actually prove this with our Kirchhoff's voltage law that this still works. If you want to do that, you take your Kirchhoff's voltage loop, and it's going to be the voltage drop across R2 plus the voltage drop across capacitor 2 has to equal the voltage drop across B, which you guys can do that on your own if you would like, but since we've already proved through Kirchhoff's current law and Kirchhoff's voltage law in previous steps that we are on the right path, that those values should be just fine unless we made a mistake in our math, which is what I just did. Okay, then the last one we have to do is we need to find the voltage drop across R3, and so that is going to be simply the current of R3, which is IC, and times R3. So we have 3.871 at an angle of 57.831 multiplied by 820 at 0. So VR3 gives us 3.174 volts at an angle of 57.831 degrees. And the voltage across capacitor 3, again, it's the current through capacitor 3 times the reactance value of it. So 3.871 milliamps, and I forgot this is milliamps, at 57.831 degrees, multiplied by the 1619 at negative 90. So the voltage for capacitor 3 is equal to 6.267 volts at an angle of negative 32.169 degrees. So the nice thing is with the scopes that we have currently, it only lets us do the one. We can't do the math functions, so it's a little bit harder to do that. We could swap the resistors around in our circuit. So on that parallel branch, you could swap those two, top and bottom. It's not going to change it, but then you could actually go through and measure the actual capacitive voltage. But really, when we have this setup, so if we were to come here and I'll scroll to the top, and if we were just to put our probe from here to here is our probe, we could measure that voltage at C2, and as long as it's what we calculated, then by all intents and purposes, the voltage across R2 should be correct because we've already proven it using Kirchhoff's law. And if one of them's right, the other one has to be to maintain those relationships. So anyway, I'll scroll back down to what we just did. So again, those are the voltage drops across VR2, VC2, VR3, and VC3. And with that, we have solved this entire circuit. There is a lot of steps, and it's a lot of repetitive stuff, a lot of going back and forth. But the key thing to remember is, what math function am I doing next? Am I adding, subtracting, multiplying, or dividing? And once you understand that, and it's just based on regular Ohm's law, that will determine what format do I need my answer to be in. Remember, add and subtract using rectangular notation, multiply and divide using polar. So that's where all these conversions are going back and forth. We just have to remember, what do I need to do next with this value? And then also, what does my answer need it to be in? Does it need to be in polar? Does it need to be in rectangular? So like I said, so that's the end of this first problem. Those are our answers. Again, if you have any questions, please feel free and reach out. I will get back to you as soon as I can. There will be one more video after this, and I'll go through one more problem. And this video itself took a long time, as you can tell. We're at our 47th minute, and so I will make this into two separate videos, so we're not looking at an hour and a half long video, and then you can go back through and find what you need to in that particular equation. We'll run through one more series parallel circuit, and then that will be it for the lecture for this week. And we'll see you guys in the next video.